Hello, everyone. Thank you for being here for the presentation. Thank you, Julie, for the opportunity. My name is Kaveh Vejdani. I'm a nuclear medicine physician, and my subspecialty is PET and MRI. I'm going to present Darmiyan to you. I'm CMPO at Darmiyan. Darmiyan in Persian means between or in between. The reason why we named that company is because we're bridging gaps in different levels of complexity in the brain, and we're introducing a paradigm shift in the world of brain imaging. This is our technical and management team. Our CEO is Padide Kamalizare, PhD. She's here in the audience. She lost her voice from a cold since last week, so I'm presenting on her behalf. She got her PhD. She's a neuroscientist by training and got her PhD from Royal Institute of Technology in Sweden. You lost my voice. Okay, back on. And is currently the CEO of our company, and she was an assistant professor at NYU before starting Darmiyan. I've done my fellowships at NYU and Stanford, and now I'm full-time at Darmiyan. I do the MRI analysis and the computer programming for the software. Thomas Liebman is our imaging expert, microscopy. He's our chief scientific officer from Karolinska, Sweden, and Rockefeller University. And Hissam Esfandiarpour is our chairman of the board. He is the CEO of Genapsys. He brings in expertise in the biotech community, and he's also an electrical engineer from Stanford University. These are some of our advisors and expanding. Charles Nicholson, the scientific father of brain tissue microstructure. We learned structural modeling of brain tissue microstructure from him. He was also the PhD supervisor and postdoc supervisor of Padide, our CEO. Paul Ringard is a Nobel Prize laureate in physiology and medicine in 2000. He's a professor of neuroscience at Rockefeller University. And Rick Rogers, Eric Lang, and Bjorn Oldfeld give us lots of invaluable advice about neuroscience and technology. So this is our product in a nutshell. It's a software platform to process brain MRI, which is the only input that the software gets. And it is the first software that detects, quantifies, and visualizes neurodegeneration in the brain. So it not only localizes the abnormality, where you have microstructural abnormality at these pixels in the brain, it also quantifies the structural distortion at each voxel. So these are the maps we generate, and we quantify in each slice of the brain how much abnormality is there. Yeah.
Are you measuring atrophy, or what are you measuring?
I'm going to explain. We're measuring at each voxel. We're measuring the architectural distortion at the microscopic scale. So it is per voxel. And it's not with statistical averaging. It is based on a computational model out of simulations that I'm going to describe. So this is actually how it's done. It is years of computer simulations of different geometries in the cell shapes and arrangements and the extracellular space and matrix. So you can simulate these structures. You can estimate what kind of an MRI signal you get in the T1, T2, and diffusion with macromolecules. And then you play with these in different scenarios of neurodegeneration. And then based on that, then you compare that with actual histology microscopy. This is what Thomas does with super resolution microscopy, where you can see the cells, the gaps, the amyloid plaques, if there are any. And then you can apply that. So we came up with a mathematical model, and then an algorithm generated based on that can process the MRI. And we test these on historical MRI data as patient progresses in the clinical stage. With Alzheimer's disease, that is our focus, is over 110 years since it was first described by Dr. Alzheimer. There's been no significant progress in the diagnosis or treatment, and the pathology was described there with the amyloid plaques and neurofiltrate tangles. Dementia is a worldwide crisis now. It is 47 million people are affected now as of 2015, and it's almost tripling by 2050. The cost of it is skyrocketing from $800 billion now to over $2 trillion. And Alzheimer's alone, the market size is about $10 billion with early diagnosis and cure. And it's been shown in different financial analyses that early diagnosis with delaying the onset of symptoms can save significantly the healthcare costs per patient and annually globally. The current clinical status, there's no pre-symptomatic diagnosis, no cure. The majority of the drug candidates fail, and each drug candidate takes approximately 10 years of time and over $1 billion of spending. And the reason is there's, again, no pre-symptomatic diagnosis. By the time the person has any symptoms of cognitive decline, the disease process is already past reversibility stage in the brain, because the brain is really a plastic organ. So as you're losing synapses and neurons, the other neurons will compensate for it. So you might have a lot of structural damage in the brain and not have any symptoms. The current clinical imaging of Alzheimer's disease, MRI, the highest resolution we have, we still use it. It shows structural abnormality. It's mainly used to differentiate the causes of dementia, being Alzheimer's versus non-Alzheimer's causes of dementia. It shows only volume change, and it's when the brain is shrunk. It's relatively late. FDG PET scan with radioactive glucose, again, patterns of metabolism in the brain cortex, and also to differentiate Alzheimer's from non-Alzheimer's types of dementia. It's low resolution, has a lot of radiation exposure, and it's late. Amyloid PET scan, relatively newer compared to the other ones. Very non-specific. If it's negative scan, you pretty much rule out Alzheimer's as the cause of patient's dementia. If it's positive, you're either due to Alzheimer's, the dementia is either due to Alzheimer's, or it could be other neurological disorders or normal aging. So very non-specific. And now our product, our software platform, is the first one to detect, visualize, and quantify neurodegeneration in the asymptomatic stage of the disease. Here's an example of a patient that was diagnosed in 2015 with Alzheimer's disease. We have his brain from a 65-year-old. We have his brain from 6 years prior to diagnosis. He had MRI for, many patients have like these MRI for five-year-old normal, cognitively normal individual. You see a lot less degeneration in the brain, kind of scattered age-related degeneration, less than 10% pretty much in all slices. And Alzheimer's patient in 2009, the same case I showed you, is the whole brain throughout all the slices. You see in different regions in the cerebellum, midbrain, basal ganglia, and the parietal cortex. Again in 2011, progressing in 2015, all of the brain involved. So the unique advantages, our platform is obviously non-invasive. It's software. It's only based on routine standard clinical MRI. No need for any tracers or any contrast agents. The only other way that it could get such map is obviously to take the brain out, put it under the microscope. So we're doing that non-invasively. It's fully automated, it's operator independent. It's real time, it's very fast. You can get these maps in a couple of minutes after you feed the software, and it's easily accessible and will be web-based for widespread use. This is our clinical validation over a public database, ADNI, with 865 brains that had all the sequences we needed, and 360 roughly cases from the hospitals we collaborated. So we're getting a recall of about 95 to 97% in both of them in the abnormal population. A little bit lower for the normal. There's some normal cases, cognitively normal cases that we're calling abnormal. Probably we're guessing because we're detecting the abnormality early, but obviously we can't be sure of that because we don't have the futures of these cases. But here's the cases that we could find that had scans for many years before, up to 15 years before the clinical diagnosis, 40 of them, and we could tell the abnormality in pretty much, in the majority of them, just a few cases we missed, we called normal. So up to 15 years we can detect the abnormality pre-symptomatic. Our major customers are the medical community for early diagnosis and when treatments are feasible. It's very sensitive. Pharma and biotech for guiding patient selection for the clinical trials to expedite drug development through inexpensive screening of the human brain and non-invasive. Research labs, it's a novel way of studying the human brain in health and disease. More information and pictures on our website. A brief overview of the past. The company was conceived in 2014. We graduated from Regional I-Corps, New York City, incubated in Harlem Biospace initially for the experimental work, and then moved to Redwood City, California, January of 2016, incorporated in September. As of October of last year, our platform is ready for service, and throughout the year we did the clinical validations. So it's an advanced ready stage technology. It just needs to be web-based for widespread global use. The product, the clinical validation is over 1,200 scans, and we've done over 100 interviews in the I-Corps with customers, and we have 25 plus early users testing it. We've been self-funded so far with initial seeds adding up to about $500K. We have an ADDF and a non-dilutive SBIR grant applications under review for about $2 million. We're currently raising 500 seed, and will be $5 to $8 million for Series A in Q3 of 2017. The milestones for the first half of this year: to expand our early users, get contracts with pharma, provide software as service for now, which we can do to early users, and we're doing, receive and implement their feedback, and get more key opinion leaders on board. We're in the process of doing pre-market notification for FDA. We filed a provisional, working on the non-provisional patent, and also working on more grants. For the second half of 2017, the milestones will be to build and deploy our web service and database. It will be available both as a web app for end users, an API for programming, and also standalone downloadable clients. The product release will be by the end of this year, and then we'll go for Series A financing by the end of 2017. Quick overview of our business model. It's going to be, again, software platform with subscription, the month of free trial, one-time 60 grand subscription, the standard medical quantitative software imaging licenses, and annual update fees of about 10 grand. Our revenue projection for 2018, we probably won't have anything in 2017 as we develop and deploy, but by 2018, with the customers, we're expecting approximately, with both pharma and diagnostics, about $3 million, and hopefully in about 5 or 6 years, we'll be up to 290 or up to roughly $300 million revenue. Thank you, and if you have any questions, answer. Right now, we only had MCI and Alzheimer's to look at, so we don't know. We're looking at patterns. For now, we can only differentiate these two. But in theory, the technology should be able to find different patterns in different diseases. Yeah.
Thanks for the presentation.
Sure, thank you.
Couple questions. I think I missed them. So are you saying that your source data is basically MRI images? Do you
Yes.
use any other additional tracer or anything?
No. Mm-hmm.
Okay, so it's basically intensity-based algorithm.
Yes.
Okay, and the reason that you can have this algorithm is because of your knowledge in the microscopy correlation with the simulation model you have. Okay.
Exactly. Yeah.
The other thing I couldn't connect the dots is your clinical validation.
Mm-hmm.
If you can go back to that slide, that would be great.
Sure.
Yeah, I don't really, so this is all retrospective.
Yeah, these are all the cases that were known. The diagnosis was known, yeah.
Okay.
It's already recorded, yeah, the database. And these one also from our collaborators, we had the diagnoses.
Clinical.
Just the clinical, just a symptomatically normal or abnormal. These abnormals are MCI and AD. Same here. Most of these abnormals are AD actually, and normals are just cognitively normal from the hospitals. Yep.
Do you have to train people to do the readouts, or do you just get like an abnormal, normal, or
Yes, it's pretty straightforward when you look at the patterns. They're very telling, but yeah, there's some minimal training involved in terms of how to characterize the abnormality.
Training is the typical Confident.
Probably a couple hours. It's very diagnostic, yeah. These ones, the larger amount of data we did with machine learning to these numbers, but for the human, visual reading, it's very easy. Yeah.
Can you just, I'm sorry, I'm still
Uh-huh.
not really connecting.
Uh-huh.
Can you just explain one row of that table, what the
Sure. Sure. So these are the cases so 650 cases were cognitively abnormal, so were either MCI or AD, and our software diagnosed 643 of them and missed 16. So we recalled abnormality in 97.6%, and these were normal, 206 of them. We called 34 of them abnormal and 172 normal, so we caught 83% of them. Same thing here. And these are probably we're guessing the higher false negative, false positive. We're calling normals abnormal is because probably we're detecting them too early. Is they're gonna develop cognitive decline, but haven't shown it clinically yet. Does that make sense?
This data would actually helpful to predict this kind of pattern for a person who is cognitively normal. You know what I'm saying?
Yeah, that's the hope, and that's that we've shown in these, because these, they already have the diagnosis. We're not adding any value here. We're just validating that our algorithm is not way off. But here's the real value that before the diagnosis was known, up to 15 years, we could show the abnormality. At the time, there was, the person was cognitively normal.
Just curious, are you, really brief question, are you still in LLC, lot number 2, why did you lose 3,000 miles? And the third one, why do you need so much cash, $5 million? It seems like the software has been validated and is ready to go.
Yeah, so first question, no, we actually incorporated in September. Two of us are, so I was moving already for my fellowship to Stanford, and Thomas is from the Bay Area. He grew up here and wants to move back. And honestly, it's more about the infrastructure and the biotech here that's not comparable to New York City. So this is really the right place to be if you want to, build something this big and make it global. And all of that cash, it's all done with meticulous financial analysis that's in terms of the expanding and scaling up, the people we need to hire for business development, for the software and graphic, and marketing and all of that. So we're going stepwise. It's at this stage, it's 500K, and then Series A will be 5 to 8, with a basically number of new people that we will hire. Do you want to add anything, Payne, to that? No, that's good. Okay.
Okay, last
Yeah.
question.
Sorry, can we go back to the chart again?
Yeah.
So,
Mhm.
the normal,
Mm-hmm.
there's a lot more people that have their normal it's surprising to me you got 34 of the normals were considered abnormal by the software. So the question is there a high correlation between something that shows this particular intensity map
Mm-hmm.
and the likelihood to get the disease? Like if you have BRCA and
Mhm.
So if you follow those patients, maybe they'll get Alzheimer's.
Well, I mean, let's look
Yeah.
back how many years for the normal. That's already a backward looking one too.
Yeah.
Well, this is a snapshot, basically. These 206 cases, at the time they had the scans that we analyzed, they were cognitively normal, but we read 34 of them as abnormal. So they were showing microstructural changes per our software, but no clinical signs for it. Not sequential, just the snap, just one time. These are the sequential ones. These are the ones that we had scans prior to their clinical. These are like 206 patients, one scan each, and we call it, and it was known whether at the time of the scan they were cognitively normal or abnormal. And we called, 83% of them correctly, and the 16.5 incorrectly. Right. We don't know for sure. We're guessing. And here, we're guessing. So this is our real evidence. This is our guess. Yeah.
Is it a good idea to know whether you have something that's not curable? Like genetic.
You can do.
And long-term care insurance.
That does actually have an answer. No, that does have an answer. Because first thing, there are interventions that can actually delay, that are thought to delay the symptom onset with good nutrition, good sleep, and exercise, which increases hippocampal volume. And also delayed onset of symptoms saves a lot of cost for the person, for the healthcare, and for the caregivers. So it's not that we can't really do anything. And the other thing is that, especially for clinical trials, the reason why the drugs fail is that they already get patients that are at the early stages of cognitive decline, which seems to be at the time that the disease process is irreversible already in the brain. So with this, we'll be able to detect, some populations that are at younger ages. You and I that might have, something, we'll be at the stage that we can actually benefit from the slowing down of the process if that drug has any effect. Yeah.
Just out of curiosity between, the current technology
Mm-hmm.
in terms of the efficiency of getting this information compared to that,
Mm-hmm.
could you give us a little difference between the current versus this cookies and this particular tool?
Yeah, so currently there's no tool for pre-symptomatic diagnosis. There are ways to measure like volumetric changes in the brain, but those are all late after you have millions of neurons lost. So pre-symptomatic, there's nothing. Yeah.
Thank you very much.
You're welcome, thank you.